All right, this is lab 8 on angular acceleration, torque, and moment of inertia. And we're going to be using our this rotational apparatus, which consists of two masses, each of a little over 500 grams, set at distances of 5, 10, and 15 centimeters away from the center, as they will be pulled by this hanging weight of 100 grams, 200 grams, and 500 grams. And what we're going to do is use this to show a relationship between moment of inertia, angular acceleration, and torque. So the big M, and I'll go through all the data. Big M is 534 grams for each. R is big R, depending on whether it's 15, 10, or 5 centimeters. The hanging mass will be either 100, 200, or 500 grams, and this will provide a torque and a tension. So this is the lab handout, which you can get from lab 8. And I'll next go through a little bit of the data of how we can take each one of these as far as analysis. So, what we first need to figure out, determine, is going to be calculating the moment of inertia for each one of these, and including the rod, which has a small moment of inertia. Then we'll measure the acceleration. I'll give you all this data after I've explained it. We'll then calculate the angular acceleration, which is A divided by 0.00625. Then we get the torque, then tension, applied torque, and percent error, which you can get, and it's the percent error of the torque and the applied torque. So these two should be relatively close if we're getting accurate results. So what I'm going to do is show you how we calculate these measurements as far as the torque. Okay, we define torque, or moment of inertia, is the moment of inertia is I equals mr squared. And for these, moment inertia is going to be the big masses plus the rod. And I've calculated that for each of these for you. For R is 0.15, it's 0.02177. For R is 0.1, it's 0.01207. And for R is 0.005, it's 0.00404. Notice how this gets smaller for each case. I will now take the data and then once we do that, I'll then go through how we did the results. All right, I've explained how to take the data of what we're actually doing here. Here's our two masses. We have them set at 15 centimeters from the center of each one. We then have weights. We'll start with 100 grams hanging, then we'll add 100 to make 200, and then we'll take that off and make it 500 grams. So for each R, we'll do 100 grams hanging, 200 grams hanging, 500 grams hanging. I'll just do a couple examples here of how we're going to take the data. Then I'll take the data and show you what I got for the results. So we'll do this. I'll do 100 grams with here. And the way we're going to do this is I will let this go. We'll use the Vernier computer, LabPro, with measuring velocity versus time. I'll collect data. So you can see this is what happens. 100 grams, rotating relatively slow. All right, so we'll start again. Make sure I get some good data. Okay. Okay, you get that. Get the slope of the line. And we get approximately 0.0015. I'll put the data all up. So that's the case there. We would then add 200 grams, repeat it. Then we'll do it with masses at 10 centimeters apart from the center, and repeat the data. And then what I'm going to do is do the last case, because notice how it went relatively slow when we had only 100 grams hanging with the R so far out, because it's much like a figure skater where arms are way out. It's much harder to turn you, but when you're farther in, it's much easier to turn you. So we'll do the last case with 500 grams, and I'll show you how fast this thing will actually go. In there. Takes a little bit of time. Okay. So now each one is 5 centimeters from the center. So I'm gonna put on 500 grams, just to show how fast this thing can really get going. We have lots of torque and small moment of inertia. And we will let it go. Notice how fast it's even hard to collect good data on this because it's rotating so quick. We have a large torque, 500 grams, and the moment of inertia is very small. So that's the data taking. We'll next do the part of doing the data analysis on the board. All right, we've taken the data and here's what we got. I here's the original data sheet of mass. Again, little m is the hanging mass. Big R are the radius of the big masses hanging out. Moment of inertia is there, and I calculated that for you, and I will show that. Acceleration is in meters per second squared. Angular acceleration is alpha, which is a divided by the radius of the little rotating rod. Torque is I times alpha. That's defined as torque, similar to what we have for Newton's second law of force is mass times acceleration, then tension, and then applied torque. And what we're going to be doing is to get the percent error, we'll be comparing the difference of these two, torque, applied torque, divided by the torque, and get a percent error, which should be relatively small. Part of the questions will ask how that happened. So here's the actual data, all right, which you can write down. I also have a photo that I'll put up with the data sheet. So these are all in SI units. So M is in kilograms, R is in meters, inertia is in kilograms meters squared, acceleration is meters per second squared, alpha is the angular acceleration in radians per second squared, torque is in Newton meters, tension is in newtons, applied torque is in Newton meters, and you can calculate the percent error. So that is the lab. You can answer the questions related to this for lab 8, and have a good day.